Good evening, everyone. I'm Banduka Kurupu, Technical Events Coordinator for Civil Engineering Sectional Committee. And this is the sixth session of our lecture series on structural design of highway bridges. And our sincere gratitude to Professor Tisan Jayasinghe for conducting these knowledge sharing sessions to uplift the knowledge of practicing engineers. And I would like to remind you all to rename your Zoom login name along with your membership number so that IESL can use that for issuance of certificates. And thank you. Over to you, sir.
Okay, thank you. Thank you very much, Banduka. So today we are planning to start the new topic, that is pre-stressed concrete. So if I tell you about my background on pre-stressed concrete, I first learned pre-stressed concrete in 1984. And that was when I was a second year student, and I had the opportunity to participate in the construction of Kaduwela Bridge. We had a earlier we had a 2-lane bridge, and before 1980s we did not have a bridge at Kaduwela, so all the people had to use the ferry or the boat. But in early 1980s, bridge was started. Bridge construction was started at Kaduwela. The design was by RDA, and it was all post tension beams of 76 feet length, and the height of the beam was about 4 feet. So they actually did all the casting of the beams at the site, and they did post tension. Then, we learned pre-stressed concrete when we were in the final year, 1986. And from 1988, I went for my PhD at Cambridge. And then again, the topic was partly on artificial intelligence and partly on pre-stressed concrete. So the examples were taken from pre-stressed concrete, and then there was a problem associated with continuous bridges, and the problem was associated with something called secondary movements or reactant movements. I will explain those things later. And if you look at pre-stressed concrete was first used in 1939 in Germany, and then people used it for many applications, various forms of applications. And with the construction of motorways in England in 1960s, they did a lot of advances with pre-stressed concrete technology, especially with precast beams, because they found that it's a very useful construction method. And when they wanted to construct continuous bridges for long span ones, they found that the design engineers always had a problem dealing with these reactant movements. So I solved that problem with my PhD, and I developed a method that allowed us to overcome the problems associated with the design of continuous bridges. So that was my background, and after that also, I taught pre-stressed concrete, continuous bridges for our MSc course. And from time to time, I got opportunities to design bridges. So one of the bridges I designed was the longest and widest in Sri Lanka. It's a flyover, and it is the Orogodawatta flyover. And then I designed 2 more bridges on A4 highway with lengths of 125 meters and 75 meters. And if you look at the 5 bridges on A15 highway on the Eastern Province, again, we were involved initially, but later we did not go. We did not complete it later because after we did the first round of designs, they found that our designs based on box girders are not acceptable to them. They wanted eye girders, and later then we said, okay, we were not interested, and later the designs were done by engineer Vijayendra from RDA, who did his MSc under my supervision when he did his MSc research under my supervision. So basically, we had the opportunity to be associated with pre-stressed concrete a lot, and so what I'm trying to do is I'm planning to share what I know with all of you, so that we can gradually build up your understanding on pre-stressed concrete and how it can be applied for highway bridges. So to start the lecture series, today we look at some of the fundamentals, and then when it comes to design, we can always stretch these fundamentals to a new level. But first we look at the fundamentals to get some idea about pre-stressed concrete, and later we see how we can make use of that for design of bridges. So today I'm going to pre-stressed concrete, and this civil engineering sectional committee lecture series, and today is 28th March 2023. So I'm making these notes because I can share the notes later. So these notes will be available for you as part of the video as well as a PDF. So we'll first look at what is the how this pre-stressed concrete was developed. Actually, people thought that by applying a stress to concrete, the behavior of concrete can be improved, because when you have reinforced concrete with some reinforcement, when you apply loads, there will be some neutral, some area in compression, and below that it's cracked. So people thought, okay, can't we improve it? Can't we improve this behavior? And so they use they did not have a very high strength concrete. So, and also they use normal mild steel. So when you use mild steel and apply the stress, sometime later they found out due to the relaxation of steel, the pre-stress vanishes. So initially you can apply pre-stress. After some time you don't get pre-stress, because due to relaxation of steel, the pre-stress vanishes. So, okay, so basically, then they started attempting this pre-stress concrete applications in 1920s, were not successful, and they gradually realized the problem is associated with steel. Then they tried So this kind of my steel. Then they decided, okay, we must go for some steel of highest capacity. So relaxation is, when you stretch steel, this is the original length L. This is L plus delta L. And with time, concrete, the steel increases its length. And gradually you find now this delta L becomes smaller. And as the delta L becomes smaller, you are losing the stress. So gradually they developed this, and then they found that they have to go for higher strength materials. So initially they went for something like 1,500 newtons per millimeter squared, and later today we have steels going up to 1,860 megapascal. So today we have steel going up to about 1,860 megapascal. These can vary from manufacturer to manufacturer, but generally, you can expect something with a maximum around 1,860, and there are some steels 1,770. There are so many different values, but generally 1,860 characteristic strength or the breaking strength steels are available. So because of that reason, we can go for about 70 to 80% of this breaking load. And at 70%, you can be very comfortable. But 80%, you need special precautions because the chances of the cable breaking when you are stressing is high. So some people actually don't go beyond 75%. And some types of steel, they are so high quality. I mean, you can go for 75% easily. And some engineers who have experience with particular manufacturer, they say, okay, never go beyond 70%. But these are, the values that we need for fine tuning. So we'll not worry about whether we go for 70% or 75%. So generally we assume that we are going to stretch it to 70%. We'll assume that we are going to stretch it to 70%. So basically what happens is, you have a steel that will have a strain curve like this, breaking at 1,860 and stress up to 70%, giving a value of giving a value of 1,302 newtons per millimeter squared or megapascal. And then what happens is, when you use it, when you apply it, the stress, initially we consider that, we are applying the stress at the center. When you apply the stress, what happens is concrete also shortens, because when you apply it, concrete can be of at a certain strength, and there can be shrinkage of concrete that can take place later, the creep of concrete, and also we get some relaxation of steel. So because of this, we get losses. We get losses because when the concrete shortens, we lose the pre-stress, and so we get losses. So as we have losses, finally you find another 30% of this will be lost. So another 70% of this from 1302 is something like 911 megapascal. So the strength of the stress in the steel is about 911 megapascal, right? So because of that reason, if a pre-stress concrete member is going to fail, the most likely point that it can fail is here. That means immediately after the application of stress. As soon as you apply the stress or transfer the stress, if the member does not fail, the chances of it failing later would be much less, because when you are transferring, we are at this level. When you are using it, you are at a much lower stress, around 50% of breakage strength. So you can see in pre-stress concrete, if nothing went wrong at the transfer as you are constructing it, if nothing went wrong as you are constructing it, the chances are that it will be very safe. It will be very safe. The chances are that it will be very safe. So that's how we have to look at pre-stress concrete. So pre-stress concrete is a very good material in that context. Then what you have to see is how much stress that we can allow in pre-stress concrete. So if you look at the earlier theory with the British standards, so we went with the cube strength. And so we know when we apply the stressors in a cube, we apply the stressors, and so you get the actual strength as 0.8 times FCU, and then when it's subject to flexure, we divide it by 1.5. Sorry. So we consider that this has to be multiplied by 0.85. So once you do that, you get 0.67 times FCU divided by 1.5. So you get 0.45 FCU. So for bridge construction, which has a special type of stressors, because when it is under, so when it is subjected to only the self weight, we get some load, and then we design the bridge for a very high load. So because of that reason, the allowable stress under British standards was considered as 0.4 times FC. 0.4 times FCU. So because we have this, the cube strength is an overestimation of the strength. So the allowable stress, so this was the allowable stress, and so under working conditions, allowable stress under working conditions. So then, if you look at Eurocode, we have this cylinder strength, which gives the actual strength, FCK, actual strength FCK. So what actually happens is, they also we get 0.85 times FCK when you are relating the cube strength, cylinder strength to strength in compression to cylinder strength in flexion. You get this, and then when you divide by 1.5, you get 0.567 FCK. So in the Euro codes, under permanent loads, the allowable stress in compression is 0.45 times FCK, but under variable loads, that means not under permanent loads, variable loads, you can go up to 0.6 times FCK. So if you take an example from C40, 50 concrete, so FCU 50, FCK 40. So this allows 0.4 times FCU as the maximum compression, which is about 20 megapascal. So under permanent loads, 40 into 0.45 gives 18 megapascal. But 40 into 0.6 gives 24 megapascal. So you can see Euro code allow me to go for a higher compressive strength when subjected to variable. But under the permanent loads, it's less than what is allowed in the British code. But when we are looking at the overall situation where you have permanent loads plus variable loads, under the variable loads, you can go for 24 megapascal. So which means Euro code will allow you a higher range for stress, and with that we may be able to generate better designs with or more economical designs the moment you go for Euro codes. So that is one of the key advantages you can notice. So then if you look at the situation with respect to the tension in concrete, the tension values were actually limited to the tensile strength of concrete. If you limit it to the tensile strength of concrete, then no cracks. So you don't have to, no need to calculate the crack. No need to calculate the crack. But on the other hand, you can stretch it a little more, and you can allow some tension and allow it to crack, and you can even go for a situation where you limit the crack width to 0.1 millimeters or 0.2 millimeters or 0.3 millimeters, depending on the type of environment. But so all these were allowed in British code as well, where we define something as class 1, class 2, and class 3. Class 3, tension allowed. And class 3 limited tension. And class 1 is no tension. So you will find most of the structures that we see have been designed as class 2 structures. But some engineers like class 3 structures as well. So you can go for tension. And if you go for tension, you must do a crack width calculation and find the crack width and see which up to which value you have to limit it. So all three are okay because what happens is when you are designing a bridge, we have the self weight. Then we apply all these loads. So the situation is that when you apply all these loads, these are the anticipated loads. They are not the actual loads. These are the loads that we anticipate. These are the loads that we think that it will act on the bridge. But most of the time, even 50% of these anticipated loads might not come on the bridge. So even if you design a beam as subjected to some amount of tension, most of the time it might not crack at all. Right? It might crack when there's a very heavy load temporarily, and once the load passes the bridge, the crack will close. So it will remain as uncracked structure. So that's what happened. So basically, if you want, you can go allow some tension, say up to about 5 newtons per meter square tension, and allow it to crack. And if you can do a crack width calculation and show the width as low as 0.1 millimeter or 0.2 millimeter, you will find that even that type of bridge can last a long time without any problem, because we calculate this stress under maximum load that we anticipate. But generally, when we anticipate loads, they are much higher than what actually happens under normal service conditions. So because of that reason, even if you stretch a material way beyond the allowable tension, you can still have a safe design. But when I am talking about this, I will consider that we are going to allow a tension up to the allowable tension or the cracking level in concrete, because then it's easier to explain the theory. So I will assume that we are going to limit the tension in concrete to about 2 newtons per millimeter square. So I'll assume that we are going to limit it to about 2 to 2.5 newtons per millimeter square, depending on the strength of concrete. But so generally, the allowable tension will be in that particular range. So I can show you some information. I can share the screen, and you already have this particular note. So this is something that I used earlier. And you can see this particular information. Now here you can see it's a cube strength. So this is the cube strength going up to 60, and this is the cylinder strength. And here you can see the maximum tension that we can allow is about 2.9 for FCK 50, is 2.7 for FCK 45, and it's about 2.5 for FCK 40, and it's 2.2 for FCK 35. So these are the kind of strength values that we generally use this pre-stress concrete. So generally it's okay to say, we maintain a tensile stress around 2.5 newtons per millimeter squared or 2.5 megapascal as general information, not the specific information. Just to pass to have some value, we can just say, the tension allowed can be around 2.5 megapascal. Right? So we can say that without worrying about the exact value, just to keep a value in our database. So we can just say, a tensile stress of about 2.5 may be okay. Right? So basically, we'll and you can see, and when you are using FCKS 50, we can actually go up to 2.9 mega Pascal as the tension. Then we also have to see, now we are talking about just a moment. (40-50) and okay, so we are talking about 40-50 concrete, and in that one the allowable tensile stress is about 2.5 megapascal. So that's the value that I'm using. So FCK 40 will give you something like 2.5 megapascal. Right. So right now our question is, how can we get 40 megapascal concrete, and how we are going to manufacture this? So if you take pre-stress concrete, what is the easiest thing to do? Apply an axial stress. Apply an axial stress. So if the area of the section is A, so we can have a section like this. And if the area is A, the force is P, what we get is POA. The stress is POA. And then what we do is we apply the nodes W, and we get a bending moment diagram with WL squared 8, because this length is span is L. So and this will give M over I is equal to sigma over Y, and we get a stress distribution like this, with this in compression, this in tension, and here due to the axial stress, we get another stress distribution like this, POA. So we can easily think about it as Civil Engineering Sectional Committee 5. So we can easily think about it as Civil Engineering Sectional Committee number 6. So POA and so there is compression. If we say compression is positive, so we can get M over Z2, M over Z1. So what is the net result? I mean, we can get many diagrams. So diagrams can be like this. So we can get a diagram where the whole section is in compression. So this is compression, this is tension. So we can get a diagram like this. Whole section is compression. On the other hand, this is bigger, compression, tension. So we can get a situation like this also. So here you get limited tension. That is also possible. And if this is less than the concrete tension capacity of concrete, we will not get a crack. But we'll have a situation where it's about to crack, but it's not cracked. It's about to crack. It's about to crack because the stress is very, very small. It's about to crack, but it's not cracked, right? So it's okay, also okay. Right? But applying an axial pre-stress like this is not very efficient. We can do better. How? So instead of applying it here, we apply it here. And then we can do this. And then this will give P. This will give a moment. Right? And the moment is equal to, if the extensity is E, the moment is equal to P times C. Moment is equal to P times C. And you can see it's acting this way. The hogging moment. Whereas the loading on the beam will give us sagging moment. Sagging. Now we can actually create a much more advantageous position where we go for P over A here plus compression, and we can create further compression, tension. Compression is positive plus, now we get, so this is P over E divided by Z2, P over E divided by Z1, because I am considering the top 5 as number 1, bottom 5 as number 2, and then I will get another diagram which goes with compression and tension as M live divided by Z2, M live divided by Z1. So the final stress distribution can be something like this, or it also can be like this. So we can get one of them. So you can see the theory is very simple. The theory is, because axial stress, axial compression can give a very favorable situation. We can use axial stress. On the other hand, we can also make it more efficient by having an excess. So now let's look at what are the situations where we like axial stress. Now you would have seen that we have these pre-stress concrete posts that CEB uses. CEB uses. And we really don't know whether it will bend this way or this way, we don't know. So what is preferred? Axial stress. So what is preferred is axial. On the other hand, we have a beam. And we know it's going to be loaded only in one direction, and that is downwards. So if that is going to be behaving downwards, what we can do is, if you know the behavior, what we do is we apply the pre-stress at an extensity and make it to bend upwards. And when you apply the loads on it, we make it to behave bend downwards. So when you apply the pre-stress, it will bend upwards. When you apply the loads, it will be bend downwards. So it's a very favorable situation because if you look at the deflection is due to vertical load W, and it will be a function of L to the power alpha depending on the type of loading divided by and the area factor K. So if you look at I value, because the section is not tracked, the section is not tracked, the I value is tracked. Whereas if you have reinforced concrete, under the same situation, here you get compression, below that is cracked. So the I value is low. Whereas in this section, I value is high because it's not cracked. So the deflections will be much smaller. And the other advantage is we can make it to start this way and then make it fail this way. That means we can apply a W, but we can apply a very high W because we start with a beam that is bending upwards. So we are starting with a beam that is bending upwards. So because of that reason, we can apply a lot of W, a huge amount of load before it actually fails. So that's why pre-stress concrete is one of the preferred materials for bridges, because in bridges we are dealing with massive loads. In bridges, we are dealing with massive loads. But just because we are dealing with massive load doesn't mean that we are going to have massive sections. So massive sections is not good. Why? Because when you are constructing the bridge, we have to lift these. So we need a crane. And cranes have limited capacity. So if the beams are very heavy, very difficult to handle the beams. So we like the beams to be slender. But there's another reason why we like the beams to be as slender as possible. Why? Because we are applying a pre-stress. And if you look at the axial component, it is POA. And if you want to maximize the stress, we have to minimize the area. Then only for a given force, we'll get a huge stress. So in pre-stress concrete, the fundamental theories minimize the cross-sectional area. Minimize the cross-sectional area. That is the theory. So always we say minimize the cross-sectional area. But you cannot minimize it all the time. So what we do is, we see how to minimize it. So we like it to be this way, and we'll have a thin web, and we can have a bottom flange. Why? Because it's going to bend this way, so we need some concrete. When it's going to bend this way under transfer, so we like to have some pre-stress, some concrete at the bottom. We like to have minimum concrete in the middle. Why? Because this concrete will not participate in flexion. It's not going to do much in the flexion because that is the area where the stresses are low. So we like the web to be as small as possible, thin as possible. But we like to have a large top flange. Why? Because it's going to carry load, and the top flange will definitely be in compression. So by having a large top flange, we can serve two purposes. So we like it to be this way. We like a bridge like that because we can allow the vehicles to use the top. So we like bridges like this. We like bridges like this, where the pre-stress is applied with a significant extension. And why we need a web is when we have a beam subjected to compression, so subjected to flexion, you get a bending moment and a shear. To resist this shear, we like to have a web as well. But this web is a penalty in the central part because the shear force diagram is like this. So here the shear force is very low. So we don't have to have a big web in the center, but we like to have a reasonable web at the end because we have to resist shear forces. So that is the logic. That is the logic. Is that clear? Is that clear?
Yes, sir.
Bandhuka?
Yes, sir. That's clear, sir.
That's clear, right? So that is the logic. Right? So always keep in mind, pre-stress concrete means we must aim for as small section as possible to maximize the axial pre-stress. So that's why you'll find that, if you look at some of the projects in Sri Lanka, and there was a very good paper published in the Society of Structural Engineers modulus, and that is about this particular bridge. The beams are like this, very slender, and that is for access for. The beams are like that. So if you look at, I think a few months ago, the modulus is the Journal of Society of Structural Engineers. They actually provided us with a very nice article presented by two engineers who actually work as in the consultant team with the consultants team. So they are given a lot of very useful information about how the designs have been carried out for port access road, and there they have used because the overall road width is 21 meters. Overall road width is 21 meters. Two box girders have been used by this Hong Kong-based designer, and the role of the Sri Lankan team was to see whether they are okay and coordinate. So, but the actual design came from Hong Kong, and they use two box girders, and the construction method was segmental, match cast segmental bridge, and so the advantage of this type of section is versus this one is that these are torsionally not strong. Torsionally, they are not good. They are not. But these ones are torsionally super because the torsional stresses will flow on a closed path like this, and there's a significant lever arm So the torsional moment carrying capacity of these sections is very high. So when you are using this in a highway bridge, these beams can be subjected to certain amount of torsion, and these box girders are super strong in carrying torsion. So because of that reason, for larger spans like 40-50 meter spans, these box girders are preferred than the eye girders. Generally, with eye girders, we can go up to about 35 meters. Beyond that, it's always good to go for these box girders because they actually give us a robust solution. Right? So we are going to talk about all these different variations during this lecture series. So the first thing is to understand something very simple, and so today we'll try to understand the basics of it and how this was developed. So for that, I will take a section. So we'll not worry about the optimization of the section. So we say subjected to force P, eccentricity E, or it can be the shape. So shape doesn't matter because we are going to talk in terms of section properties, and the section properties will be I, area. So I is the second mode of area. So we are going to talk in terms of these properties. So we are not going to worry too much about the shape because we are going to make use of the properties. So whenever we want this, we need to have a sign convention. So the distances measured upwards are called y1. Distances measured downwards are called y2. And y2 is positive because y2 is positive, y1 is negative. Then if you look at the top fiber, we call it fiber number 1. Bottom fiber, we call it fiber number 2. So in that case, if you take Z1 is equal to I over Y1, because Y1 is a negative value, Z1 is a negative value. Z2 is equal to I over Y2, and Y2 is positive, so it's a positive. Right? So
Sir, you're on mute. Could you please unmute yourself?
yeah. Okay. Now you can hear me?
Yeah, thank you.
Yeah. So basically here, we all use M over I is equal to sigma over Y, and that is the building the formula that you have ordered. And with that, we can say M over Z is equal to sigma max. So we make use of this formula a lot when you are dealing with pre-stress concrete. So now what we do is we will look at how to make use of this formula. And so I will take a section. So this is a section, and let's say the neutral axis is there, and this is y1, this is y2, and this is z2, and this is z1, and I'm going to apply the pre-stress at an eccentricity E. We are going to apply the pre-stress at an eccentricity E. So what happens is, when you do this, we get a section subjected to force P at an extensity E. So what actually happens is, first we get P over A. So we get P over A. And this is positive compression. Plus PE over Z2, PE over Z1, and we look at what happens. So here it goes into tension. This side tension, this side compression. Tension and compression, this is also compression. So this is positive, this is negative. So if you look at P over Z2, Z is positive, so you get a positive. If you look at P over Z1 is negative, you get a negative answer. So what you say is, so this is plus this. So if you look at the stressors at the top fiber, what you get is P over A plus PE over Z. If you look at bottom fiber, what you get is P over A plus PE over Z. And then we add again M over Z2, M over Z1. Why? Because here you get compression here, tension here, and this is negative, this is positive. So to get a negative answer, we have to introduce a negative sign here. To get a positive answer, we have to introduce a negative sign there. So you get minus M over Z1. Here you get minus over Z. And what can happen? So when you apply a load, it can fail this way in the top fiber, or it can fail this way in the bottom fiber. Fail that way in the bottom. So if you apply a minimum moment, then this is this situation. So this at transfer. That is at transfer. This at service. So at transfer, what you get is only the dead node. And when you have only the dead node, it is this situation, that is situation number 1, this is situation number 2. So when you get situation number 1, what you get is, should be, so the top fiber can fail in tension. So this should be greater than tension at transfer. And then, now this is going to fail in compression. Bottom fiber is going to fail in compression. So this should be less than compression allowed at transfer. So we can write two equations. Is that clear? So basically, what we have is a
Sir, we can't hear you.
We use long line method, and we cast beams like this. One after the other, we cast beams. And what happens is, so we cut the wires after concrete has gained strength, but concrete has not gained all its strength. So that is the initial strength of concrete. So what we do is, we cannot allow, we have to allow some compression, but we are in the strength development curve of concrete, and after 28 days, we might get some good strength, but we are here, somewhere here. So we may not have all the strength that we need. So if you are using 40-50 concrete, at the transfer, we might specify the concrete should reach about 30, or here corresponding something like 35. Right? So we have to specify a strength. So it's a lower strength. So on the lower strength, we can say, because these stress diagrams are triangular in shape, we can allow 0.6 times 30. So that means we can allow a stress of about 18 under transfer conditions, right? But still the concrete has not reached its maximum strength or specified strength, because if we are to reach the maximum strength or the specified strength, we have to stop manufacturing of beams and wait until concrete gains the adequate strength. So because it's difficult for us to do that in a profitable way, so what we do is we specify a lower strength and say you can stress it at an early stage of strength development. So after about 7 days of casting the beams, you will find now it has reached 30 megapascal, or after 4 days of casting the cubes, casting the beam, you will find the cylinder strength is 30. Then you say, now it's okay. Let's cut the wires and make the casting bed free for next batch. So that's why we don't wait until the concrete has gained its full strength to do the pre-stressing transfer. So we always do it at an early stage. So if I look at it in full context, so we have two situations. One is transfer. So we have POA, we have PE over Z, we have MD over Z. And then we have service. We have POA, PE over Z, MD over Z, and M live over Z. Now we have placed it and we are applying more loads. So you get the live load moment as well. So initially beam is at the yard, no live load movement, only the dead self-weight. Now we have lifted the beam and kept it and finished the bridge. Now we get dead, and we can also get two deads. One is the dead that has applied as the self-weight, and then we can get another dead. So we'd say MD1 and MD2 always say. So we are getting an additional component of carpet that we place on the bridge, or some screen that we place on the beam. So whatever the dead loads that we are going to apply later. So what actually happens is, now this stage, the beam is like this, at top in compression, top in tension, bottom in compression. Now in this state, the beam is going to fail like this with top in compression, bottom in tension. So this is the theory, and then now we can write two sets of equations by looking at these equations that we have already seen. And if you look at the transfer. So in addition to that, because once you do the transfer, there will be losses. So the P becomes R times P, where R is about times. That means we lose about 30% of the stress in the tendons once we do the transfer. And with time, we are going to lose about 30% of the stress. So I showed you at the transfer, we get about 1,300. And at service, we get about 900. We get about 930. We get about 930. About half the stress. So 900. So which means we have to apply a factor called R, which represents the losses that occur after the transfer. Now we can write two sets of equations at transfer. POA plus POZ1 minus M over MD1 OZ1. And what is the failure you get? Now this is the top fiber. One is top fiber, two is bottom fiber. One is top fiber, two is bottom fiber. And it's going to fail in tension. So we say it should be greater than tensile stress at transfer. And if you look at the bottom fiber, POA plus PE over Z2 plus minus MD1 over Z2 should be less than compression stress at transfer. So this is equation number 1, this is equation number 2, and then at service, it is going to behave like this. So you get POA plus POZ1 minus MD1 over Z1 minus MD2 over Z1 minus M live over Z1 should be, now it's going to top fiber. We are talking about top fiber, it's going to fail in compression. So it should be less than compression allowed under working conditions. Compression allowed under working conditions. So then you can write the same equation for bottom fiber. Z2 minus MD1 over Z2. Here you can see MD1 over Z2. We have already written it. Minus MD2 Z2 minus MNO Z2 should be greater than F tension under working. So I am saying minus 2 is greater than minus 3 because tension is minus. So we have to say minus 2, this side should be minus 2 and it's greater than minus 3. Right? So because tension is minus. Whereas compression is, so here you have to say 17 is less than 18. 17 is less than 18. Whereas in the tension one, we have to always say, right? So, always say that is 0, minus 2 is greater than minus. So we get this situation, and that is which number? 13. Series section 13. Now we can rearrange these equations. Equation number 1, 2, 3, and 4. This is number 3, and here you get number 4. So we have 4 equations, and we have to rearrange the equations. So what we do is first I will rearrange the first equation. So here you can see P over A plus PE over Z1 minus MD1 over Z1 should be greater than FT. Then I can say PE over Z1 should be greater than minus P over A plus FTT plus MD1 over Z1. Right? So I can write that equation, and then I can say I multiply this whole equation by Z1, divide it by P. Divide it by P. Then I can say E should be. Now you can see here I am multiplying by a negative quantity. So I am saying minus 2 is greater than minus 3. But if I am going to multiply it by 2 minus parameter, then I have to say 2 is less than. So the inequality should change. Is less than. Is less than minus Z1 only. Minus Z1 FTT over T plus MD over T. So I'm going to write E should be less than minus Z1 A plus 1 over T MD1 minus Z1 FTT. T should be less than minus Z1 over A, 1 over P, MD1 minus Z1 FT. So this is the first equation. And you can see this Y is equal to C plus MX. And X is 1 over P. And this is the gradient. M is the gradient and it is given by this. And C is the intercept, it is given by this. So if you look at this one, then we can say, if we draw a diagram with this as 1 is to P, 1 over P, this as P, Z1 over A minus Z1 over A is positive because Z1 is negative, so this is minus Z1 over A. And we are going to get a line like we are going to get a line like this. So this was first represented this way by a person called Magner. Actually, it's a real name. This is a Belgian guy. Although we write it as Magner, they add all these dots and so on. So his actual name is Manier. Manier. So all over the world, people call it Magner diagram. But because we write it as Magner, but his name is Manier, so it's actually Manier's diagram. So Manier is the first person, Belgian engineer, who invented this graphical representation of pre-stressing equations. Now we see what happens now. So this is called Manier. The name of the engineer is a Belgian engineer. He's the one who invented this, and his name is Manier. But in English we write it as Magner because we don't have dots and other things to modify the way that we pronounce in English. So we just write it as Magner, and everybody in Belgian language also it is written as Magner, but they used to add some additional symbols to indicate how you pronounce it. But in English we don't have it, so all over the world now it is this diagram is considered as Magner diagram. So now you see that we have equation number 1 will give us this equation. So E should be less than minus Z1 over A plus 1 over P MD1 minus Z1. Z1 FT. Z1 FT. So if you look at the second equation, again you can see E is less than minus Z2 over A plus 1 over P M D1 minus Z2 F CT. This is equation number 5. This is equation number 6. Now, if you look at the last two equations, you will find E should be greater than minus Z1 over A plus 1 over. Now, when I am writing, I should have written as RP because we have the losses when under service. So, you get 1 over RP. Now, here you get MD1 plus MD2 plus ML minus Z1 times SCW. And here you get E should be greater than minus Z2 over A plus 1 over RP MD1 plus MD2 plus ML minus Z2 FTW. So we get equation number 7 and 8. So if you look at this diagram, you can see this is Z1 over, this is Z2 over. So we can draw it as 1 over P and extend it this way. And this is Z1 over A minus Z1 over A. This minus Z2 over A. Because we know Z2 is positive, minus Z2 over A is negative. So we get two equations. And we get another two equations. And this equation from Z1 says Z1 should be, E should be less than. So this is equation number 5. And second equation says E should be less than. So that means this is equation number 6. And this is equation, E should be greater than. So this is equation number 7. And this is equation number 8. So these two give regions like this. So we say this is the feasible region, but when we have a section, this is the centroid, this is the eccentricity E, we can have a maximum value for E, so we have to mark that. This is the maximum eccentricity from the center, maximum E. Why? Because we can't place tendons outside the section. So we can say this is the feasible region. And if you select any point on this, what is going to happen? Any point on this will finally satisfy all stresses. So you select any point on within this space. Within this space, all 4 equations will be 6. All 4 equations will be 6. If you select any point here, some of the equations will not be satisfied. So this is the graphical representation, and in the English-speaking world, it is called Magnol diagram. And if you go to his original country Belgium, it will be called Magnol diagram. So this is the theory of pre-stress concrete. This is the theory of pre-stress concrete, and you can see, this is the basis that we use when we are designing pre-stress concrete beams. Because we don't worry too much about the equations, we simply draw the equations as a diagram, graphical representation, and then we select a point inside. Bandhuka, is it clear?
Yes, sir. That's clear.
That's very clear, right? Okay. So, now the time is 8:21. So, because we have to finish it around 8:30, shall we ask whether they have any questions, any problems they would like to ask?
Yeah.
And continue from that point next week.
Yeah, that's good, sir. And you can
Anything
ask
in the chat, sorry?
Yeah, participants can ask questions in the either chat box or can unmute and ask the questions.
Yes. So they can ask anything, any question. Only thing is okay, chat box. We have joined here. You may. If somebody says it's better if I can share the previous day lecture notes, I have already done it. Bandhuka?
Yes, sir. Three lectures done. And then this one and the previous one we will be shared.
Yes.
Up to 5 lectures we have shared. This one
Yes.
only. Yeah.
Yes. Actually, somebody is asking whether I can recommend a book for cable state brick design. I cannot remember offhand, but I can certainly find and let them know. Tracking MD1 moment, shall we consider top stamp also? All right, okay. That's a good question. So basically, now what I have done is only the not composite construction, composite. That is this is only pre-stress. And something like this, a bridge consisting of a situation like this. But now there's another type of construction. That is, we cast beams like this and place them at a spacing. And then we are going to add the top flange. And this is called composite set construction. Right? Composite construction. So I will discuss this next week. Because composite construction, the equations are slightly different. Because once you add this one, the overall centroid of the section, originally it was somewhere here, now it is there. So the centroid changes. Because of that reason, we have to look at it in a slightly different context. So I'm not going to talk about this today. I'm talking only about something like this, a very simple situation where we place some asphalt concrete or street and some asphalt concrete and use the bridge. So this is not a situation where we are having specifically cast top slab, right? So here we'll cast a top slab of 180 to 200 millimeter, and it is specifically cast. Here we are just having a screed and some carpet. So we are looking at a very simple situation, and in Sri Lanka also we had a simple solution for a bridge like this. It looks like this, very shallow section. And what we did was, whenever we want a bridge up to 6 meters of length, we took all these beams, placed them side by side, like that. We put a tie wall here, tighten here, and then put some asphalt here. Bridge is over. So I'm talking about this type, right? But next week I'll talk about this one. Okay. So basically, here the MD1 is this one, the weight of this. MD2 is the weight of asphalt. Now, in this particular one, this is MD1. This and addition. Once we add all these things, we'll get MD2 plus asphalt. All that is MD2. So here MD2 is only just the addition of some asphalt. So I'm talking about this particular situation where the centroid of the section does not change for live loads. It's the same centroid for dead loads and live loads. Whereas here centroid changes. Centroid of the section changes because original centroid is here. Now after casting of the composite slab, the centroid changes. So I'm not talking about this particular case. I'm not talking about this. I'm talking only about this case. Is that clear? Yes, Madhuranga. So I have clarified that, right? Okay.
Okay, sir.
So basically,
I understood.
Yeah. Okay, good. Right. So now what we do is 16. So what we are going to do is, we can always draw a diagram like this, and this is how we draw it. Little awkward because we have the so this is 1 of P and this is C. We have the eccentricity measured downwards, and you know the reason, because if you take a section, we measure the eccentricity downwards, E downwards. So we draw it also, this diagram also is drawn downwards, and this is at 1 OA, this is at 2 OA. Again, you can see Z1 is negative, minus is positive, so this is a positive quantity. And from Z1, you get equation number 5 saying it's governing, equation number 6 saying it's less than, then equation number 7 saying more than, equation number 8 saying more than. So that means Z on this side. Then we have a maximum extensive parameter that is saying that we have to have this inside, we can't have it outside. So there's a maximum limit we can go. So once you do all that, we get this region. So the moment you select a point inside, you don't have to check stresses because all 4 inequalities are satisfied by any point inside this shaded portion. So you don't have to do anything. You can just select and you don't have to even check the stresses. But when you are selecting the stresses, now you can see this is the minimum pre-stress force because this is 1 over P. Here you get the maximum pre-stress force. Now which one we like? Minimum or maximum? We like this. Why? Because it's going to fail like this and it's fail in tension. When you use this maximum, how can it fail? It will fail at the top fiber with crushing. Which one is better? Crushing of concrete or yielding of reinforcement? Tension. Cracking in tension or crushing in concrete? Which is better? Always, a tensile crack in concrete is better because it gives us the warning. Right? So because of that reason, when you are selecting, we always like to select as close as possible to the minimum, as close as possible to the minimum. Why? We know these pre-stressing tendons are expensive. So because of that reason, it's if you want to have an economical solution, we must always go for a minimum value given here. Minimum value given here. It should be as low as possible. So that's the reason why, when you draw this diagram, not like using equations, you can straight away say in which region we should be selecting the pre-stressing force. And we should select the pre-stressing force as low as possible, because then when the pre-stressing force is low, when we apply the full loads, the beam can crack, and when the beam cracks at the bottom, the yielding of steel will occur, and we'll get plenty of warning that something is not right with the beam. So we have enough time to evacuate. But if we go for the maximum pre-stress, it's very expensive because we have to create a massive pre-stress. But the problem with massive pre-stress is it's going to fail in compression. You're going to fail in compression, and you will get a sudden failure of the beam. So we always like to use the minimum pre-stress. Is that clear? Bandhuka?
That is clear, sir.
Bandhuka?
Yeah.
It's clear, right? So always select a pre-stress as low as possible, Then you will get a very good situation because you are not going to waste any money unnecessarily. And you should know, concrete is a natural aggregate-based material, and we use the only factory manufactured material is cement, and we can use fly ash, which is a byproduct. And so basically, we are getting a high strength by using admixtures and reducing the water content. And so if you look at the cost of concrete and cost of pre-stressing steel, we all know pre-stressing steel is about 2 to 3 times, can be 2 to 3 times more expensive than the reinforcing steel, because although it's the same steel, this steel has been subjected to a special manufacturing process. Because of that reason, it gives a strength of 1860. Whereas reinforcement is manufactured with some modifications, and we generally limit it to 500. So you can see this is about 3.5 times stronger than reinforcement, and we have to pay a cost penalty. And cost penalties, the cost of pre-stressing steel can be about 2 times the cost of reinforcing steel. Right, so pre-stressing steel is about 2 times the cost of reinforcing steel. So even in reinforced concrete structures, we try our best to reduce the amount of steel. Now in pre-stressed concrete, we should be trying even harder. So because of that reason, we always try to concentrate in this particular region that is giving the minimum pre-stressing force. Right. So that's how so I'm trying to develop your understanding on the logic. So it's very important we learn the logic, and once we know the logic, we can always go for very complicated or very sophisticated designs the moment you understand the logic very clearly. Okay?
Okay, so there's another question.
Yeah.
Will there be any changes in the equations between post-tension and pre-tension? How to avoid the sagging moment effects near the supports?
Sagging moment effects near the support in post-tension. Post-tension and pre-tension equations are the same. But what differs is the loss calculation method. And when you are talking about sagging moments at the support, are you talking about continuous construction?
I think so it is continuous, for continuous.
Yeah, so continuous construction is a completely different scenario. So we'll talk about it later. I'm going to teach how to design a continuous bridge. So when we come to that, we'll talk about all those specialties. Okay, because at the moment we are talking about very simple cases because we want to build up our understanding on pre-stressed concrete starting from the scratch, because many of you have some understanding, but when we start from the scratch and present these theories very clearly, we can actually go a very long way with a great deal of understanding. So today we'll not talk about this continuous one because continuous ones have to be handled in a completely different manner, right? The equations are the same, but the way that we approach it is very different, right? These basic equations are applicable for almost every case, even a continuous bridge. These basic equations are applicable. So that's why I took some time to develop the equations with and also the manual diagram. Okay. So with that, Bandhuka, shall we conclude the lecture?
Yes, sir. And for the new participants, they will keep asking about the past recordings and study materials. So we have shared a link for the WhatsApp group. So all the previous recordings and study materials will be shared again in that same group for the new participants. So just join that WhatsApp group. And I would like to invite Engineer Gobi for the vote of thanks.
Thank you, Bandhuka. I would like to extend my thanks to everyone who made this webinar on the structural design of highway bridges possible. We are grateful to Civil Engineering Sectional Committee for organizing this informative session. First and foremost, I would like to extend a heartfelt thanks to our esteemed speaker, Professor Jayasingham, who took this valuable time to share his knowledge, expertise, and experiences with us. His webinar series is informative, insightful, and thought-provoking. It has undoubtedly enriched our understanding of the structural design of highway bridges in the field. I would also like to express my sincere gratitude to Engineer Kamala Gunavatna, the chairperson of Civil Engineering Sectional Committee, for her support and encouragement, and Mr. Bandhuka to organize and coordinate such useful events continuously with full of energy. Our thanks also go to the IESL Secretariat, Publicity Department, and IT team for their effort in promoting and hosting this event. Finally, that next session will be held on next Tuesday. We hope to see you all there for another enlightening and informative session. Thank you all once again for your participation and support. Thank you.
Okay, thank you very much.
Okay. Thank you, Gobi.
Thank you very much.
Thank you, everyone. Good night.
Professor, thank you.
Thank you.
Thank you very much, sir.
Thank you.
Good night.